是好，OK，好，大家不用担心啊，这个我们等最后会一起看。不过对啊，大家可以或者学期末一起来看大家状况怎么样。不过是有点出乎意料，不过大家可以再仔细看一下说，对，这就是哪边有一些问题，可能对看一下这样子。我还是觉得大学的时候是都没学好。Anyway, so we'll continue. We'll continue on the basic questions of HML. Again, repeat, recap. Okay, the reason that we have HMA is basically we're moving into statistical data-driven ASR system where we already talk about features, front-end parameterization using MFCCs, and then again, recognizing text basically means, okay, taking a speech waveform, mapping the features to actual sets of symbols. And the symbols are actually coming from the phoneme, the pronunciation of each of the word. Okay, so each of the phonemes will have a acoustic model that to represent how likely it has been uttered from that particular phonemes to see the features that you see. Okay, so it's a basic a sequence to sequence mapping. If you think about this, it's a sequence of acoustic feature to a sequence of phonetic symbols. Okay, and then we introduce the HMM because we know that sequence to sequence is a many-to-many kind of mapping because every such of phonemes can have different duration. So it's not a fixed sequence to fixed sequence. Okay, there's a durability, there's a durational variability there. And then because the statistical model, and that means the features that we see follows a distribution, not static, not deterministic rules. Say, okay, R will see this to FCC. Okay, you'll see R in various kinds of MCC that kind of behave like a particular distribution. Okay, so there's some variability in terms of the spectral feature value stuff. Okay, so that's why we introduced the HMMs. I think we talk about the first question. So basically, the three basic questions of HMM. Given observational sequence HMM and model. Okay, the model HMM has parameters of transition matrix. Okay, output probability. We call it emission probability parameters. Initial state parameters. Okay, if you're using Gaussian mixture model, you have the N and M. Okay, the number of state you have for the hidden model to transit in different states. The M tells you how many mixture you have per Gaussian mixture model within every of the state as being represented as the beta. Okay. So the first question we want to ask about HMA is how do we compute the total probability of a particular observational sequence, the probability of observational sequence given the model. Okay, so this kind of idea is called scoring. Okay, you have the notions of how well a particular model matches the observational sequence. Okay, the classical use of this kind of computation of this probability is used for recognition. Okay, you have a set of competing models, and you find a model such that this probability will be the largest. Okay, so then you choose that particular model. So it's being used for scoring against different models and pick the best model. Okay, so for question 2, right, given an observational sequence and HMM model, how do we choose a state sequence? Okay, which is usually hidden, and Q1, Q all the way to Q that best matches the observation. In general, there's no correct answer or even a unique answer. We will use our optimal criteria to choose a state sequence. And the reason that we need this sort of best state sequence decoding is for use to continuous speech recognition. Okay, so it's not just a fix. This is if we string together all these sequences become a word, become a sentences. Okay, you need continuously decode finding the most probable hidden state. That process we need to find the best matching state sequences. The third is we call the training, right? Given a model, a set of parameters. Okay, how to use data observation to derive from each of the model or each of the class to train your HMMs. Okay, at the training, some people call learning. Then you can use this model to perform recognition or to compute the P of all given lambda, right? And also to find the best state sequence. You need the actual values of listings. How do we know what's the best value for each of the class, for each of the phoneme? Okay, then there's a learning that needs to take place in this case. Okay. We did mention problem 1. We'll go through this very quickly, and today mostly we'll talk about the second problem. Okay. So again, the problem 1 is trying to calculate the total probability of a particular sequence, right, under this model. So you have HMM model. You have a sequence observation, want to find the total probability of this observation under this particular. Okay, so go through this quickly. So if your model has n state and there's n to the t power possible state sequences, okay, it's not possible to go look through all one of them and pick the one that's the, and then sum it up all those probabilities. So we will find a way to actually compute that faster. But anyways, given a particular state sequence Q1 to Qt, if the probability of known state sequence, okay, we're trying to find probability of total observation given the model. Okay. If I do know the state sequence, okay, originally it's hidden, actually one path action known. Then the probability is just probability t from 1 to t, p of ot given qt and lambda. What that means is this product. That means over time, once you know the state sequence, across time still become independent, right? That's why you have this multiplication. Once you know the state, okay, the time and time different, the time and time that there's the joint distribution factors into product. So once you know the state, the probability becomes a product. Okay? So observation is statistically independent if you do know states. With hidden Markov model, we don't know the state. So if we want to find the total probability of the observational sequence, we need to look through all the possible state sequences. All those possible hidden sequences, sum it up, that becomes the total probability. If I do know, that's the probability. Okay, so we just need to know, okay, that's the probability becomes a product of the observational sequence. If I know this is the first state at the first time, I just need to know the probability of you are in first state and then you outputting observational symbol at first time, right? Now also the second time point, okay, if you're in a particular state, I just need to know the probability of that when at the second time point in that particular state you're seeing the observation to multiply that through, that gives you the observation sequence, the probability given a particular sequence under this particular model. Okay. But then what's the probability of this particular sequence, right? If I know a sequence, okay, what's the probability of a sequence, a known sequence state under a hidden Markov model? Well, it's pretty easy, right? The initial state probability, right? When you start, you're in Q1, okay. When you're in Q1, you go to Q2, or when you Q2 go to Q3, okay, this transition matrix, okay, this sequence of probability tells you the probability under this model, you see that particular sequence, okay? So the total probability is very simple, right? Total probability is just the sum of the joint probability evaluated over all possible state sequence. So we know what's the probability of a particular state sequence. We know if I under that particular state sequence, what's the probability of the observational sequence. So what's the total probability of this observational sequence? Just sum up all possible state sequence, all of them all together, and you have P of O given lambda. So the idea, right, that becomes the sum over all possible state sequence, right? The probability of that state sequence, the probability of when you're in that state sequence and also seeing that observation. Okay, sum up all those things give you the total probability. Right, so if you compute this probability directly, we know that it becomes almost impossible, right? Imagine a case n equals to 5, t equals 100. Okay, that's not very long sequences. But you have sum over this thing is basically 2 to the 100 power sequences you want to sum over all these summations. Okay, and too many of those state sequences you have to sum over. Okay, so it's pretty difficult. So we introduced a concept called a forward algorithm. So it's an efficient algorithm to actually compute this probability. Okay, the reason why there's so many redundant calculations, right? Because imagine a sequence go like this, another sequence go like this. Okay, when you compute this probability and this probability, the first couple slides, the couple states time, they share the same state sequence. We have to recompute it all the way through. Okay, so that makes this redundant calculation quite a lot. So we need to reduce that, okay, basically by introducing some variables that try to capture every possible information up to this point and just move it on one at a time. So when you move these variables one step at a time, and that variable captures every possible probability up to that point, okay, then it becomes easy to compute this total probability. So we can introduce a forward variable, okay, it is still a probability. Okay, we should say of alpha ti. Okay, alpha ti means the probability of the observational sequence partially up to t. And also in that particular t, you're in state I under this particular model. So in plain words, alpha ti is the joint probability of the partial observation up to the point t, not the capital T, the point t. Okay, and where your state t, okay, is actually I given this model. So we can have in this, then you can do iterations. If the first time, right, is alpha 1I, P01 Q1 equals I plus lambda. So what's this probability? It's just initial state probability because you're in I state, initial state probability that you're in I. Once you're in I, the output probability when you see the observational sequence at the first point is 1. Okay, right? And you do induction. Okay, for t at t plus 1, okay, this alpha variable alpha t plus 1j, okay, equals sum over alpha ti aij, because this accounts for all the probability up to the point t and qt equals to I, right? So this probability, right, ati, this variable is a probability. Okay, this is just the probability of partial observation up to ot, and then you're in t, and then the state, the hidden state that you're in I. So the next variable is say, okay, the next time I'm going to be in j. Okay, so what's the probability of my next time I'm going to be in j? Well, you have the current time you're in t multiplied by I go to j. Okay, and you sum over all possible i's within the current time, right? So all the I state can go to the j state at the next time. Okay, so what's that? Probably just sum over all these things. And then this forward variable account partial observation up to t plus 1. So you still need to multiply by the output probability of the j state when you're in j state. Okay, and next time you see the observation on t plus 1. And you just continue to do alpha t plus 2 in relation to alpha t plus 1 for all I, for all t time from 1 to t minus 1, or j, the state all from 1 to n. Find the number of hidden Markov model states. Okay, so this forward variable, right, essentially every time it captures all the information, all possible ways, all probability mass up to that point within that particular state. So I want to move on this forward variable, move on to the next time point at a particular j state. Okay, you just need to sum over all possible state in the previous time and move into this particular forward variables at t plus 1 in j state. And multiply by the partial observation up to that point. So multiply this observation and just continue to roll until the ending point. Okay. At termination at t equals to t, then you can compute the probability of the total observation. Okay, given that n equals to at the final time, just sum over all the state. This forward variable evaluated at the capital T, all I state. Just sum it up and you get the total probability. Because you think about this forward variable essentially captures all possible state sequences probability all the way to the end. And you just sum up at the end point. Okay, then you get the total probability you see in this observation. Okay, so that's the basic idea. Okay, again, I talked about this already, so I'll skip this. Right, so at the end, right, is the joint probability of all possible state values with all accompanying partial observation. And the number of calculation now becomes n squared t. Okay, it's much less. Okay, usually state number is 3 or 5. Okay, that's minimum. Okay, t if it's 100, that's fine, right? 3 to the square or factor square is 25 by times t is, and if it's 100, then it's only 25,000. Okay, so 2,500. That's much fewer operation you need, okay, compared to n to the t power. Okay, so basically hugely reduce the number of calculation you get, and you get an exact amount. So this is not approximation, this is exact. Okay, basically by changing the ways we compute probability by introducing the forward variables. By introducing a forward variable, it makes the whole computation okay, extremely fast and quick. So the basic idea, again, going back a bit, the idea is very simple because each of the n possible state at time t plus 1 can only be reached from any one of the previous n state at time t. Because of this, so you really don't need to always look from t1 to t to capital T. You just need to do one step at a time. Okay, because if I were to go to the next step, I cannot go back 2 steps back. I can only go 1 step back. So I'm only possible to go from here to here. Okay, I'm not possible going from here to here directly. Okay, so there's no need to recompute all these things. You only need to compute it once because there's no possibility that you go here and suddenly jump, go to t plus minus 2 and jump to t. Okay, because of the Markov first order Markov assumption that we make to hidden Markov model. So any point in time, you can only count from one of the point in the previous time. Okay, so if you can compute all the probability up to one point time in the previous time point, then that's all you need. Okay, so that's the basic idea behind forward algorithm. When you have forward, then you have backwards. Okay, so again, it's very similar idea. Go through this very quickly. So you define a backward algorithm. Time t, it counts for partial observation for t plus 1 all the way to the end, given qt equals I and lambda. Probability of observational sequence of t plus 1 at time t plus 1 to the end point. Okay. Then again, you can iterate. Okay. You start at the end. Okay. B of t, capital E, equals 1, I from 1 to n in different states. So you go backwards. So bti, right, equals to, right, the aij, because they're all the j's go to I. Because going backward. Okay. So t, you're in time t, you're in state I. That means all the t plus 1, one of the t plus 1 goes there. Right? One of the t plus 1, basically all the j state in the t plus 1 go to I state. So all of them are aij, right? All the possible ways. Aij is basically ji, the same thing. Aij, aj, and multiplied by bj, right? All t plus 1 and beta, right? The partial observation of bt plus 1j. Okay, so you multiply this variable will account for all possible partial observation from t plus 1 to the end, and then also how you landed in this particular state, where at time t your qt equals to I. Okay, so you do this for all t from t minus 1 all the way to 1, from I from 1 to n. At termination, right, you backtrack at the termination, where you actually at the beginning of the point. So you just sum over all states, initial state probability, your observation at the first state, okay, at the first time through all the states, okay, and multiply by the backward variable evaluated back to the time equals to 1. And you sum up all these things, it gives you P of all given lambda. This is the, again, total probability given this model. This number is the same as that forward algorithm. It's the same as you enumerate all possible state sequences. These three algorithms give you exactly the same answer. This computational complexity is the same as the forward algorithm. It's just one is going from forward, another one is going from backward. Okay, they both are basically the same answer. Okay, the same idea is very simple, right? You can only backwards, okay, you can only backstep, okay, from the t plus 1. You cannot go to t plus 2 and suddenly jump back to t. Okay, so to be able to be in one of these states, you have to have come from one of the n state in the next t plus 1. So if you can compute all the probability up to this point, then it captures everything possible over there. So you don't have to recompute all those things. And then you just sum up all these things and go here. Okay, these two things gives a redundancy computation, reduce the redundancy computation by quite a bit. Okay, let's review. Let's go into the second questions, right? We want to find the optimal state sequence. Okay, first question is scoring against the model. The total probability of me seeing the observation. Okay, the set of sequence of MSCC given a model at HMM. Okay. Now we want to find the optimal state sequences, right? So again, the first problem, if you recall back to the coin tossing example, okay, scoring against model basically is, your friend don't know whether your friend is doing the head bias coin or tail bias coin. Okay, that's scoring against these two models, and you find which one is good. State sequence decoding is basically trying to tell, okay, whether it starts with a fair coin or unfair coin. Okay, if it's flip fair coin, then flip unfair coin. Okay, which of this is most likely? Okay, so the state sequence tells you their actual actions. Okay, the scoring on the first problem tells you overall which model is more likely to generate the head and tail seek. Okay, so understand the details different between these two problems, and this is how we set it up. How do we find the optimal state sequence if we even define a particular way of defining a state sequence? So if you say we call it local computing, okay, let's try just find every time step, okay, look through all the steps within every time step, which probability is largest, okay, and then we look at every time step, look at every state, okay, and that's the probability of you're in that particular state. Okay, then we can find, pick the one that's largest at every time point. That's, a intuitive way of of looking at things, right? So let's work it out. If we were to do that, what would it look like? Right, let's define a new variable called v sub t of I, right? Imagine all this HMM, you always have this dual index, okay? One index is state, one index is time. Okay? Imagine you have a variable called VTI, okay, that tells you the probability of you're in this particular state given the total observation, right? The entire sequence of observation for each of the time point, what's my probability that you're in one of the state? Okay? If I can compute this, right, for every t from 1 to t, okay, look through every t, find the one that's largest. Okay, maybe there's one way to pick the most likely state sequence. Okay, so basically finding the most likely state for each of these. So that's probably a B in state I at time t given entire observation. So to be able to compute this, Bt of I means probably a Qt equals I given observation, entire observation, the model. Can we write that as probably O and Qt equals I and lambda. So entire observation and at time t, you're in state I, okay? Divided by the total observational sequence probability. Okay, how do we compute this, right? Let's look at the numerator P of O and Qt equals I is just P, let's spread it out, right? O1 to OT, Qt equals I, OT plus 1 to OT, this joint probability, right? Given this model. Now we can rewrite this as P of O1 to OT, Qt equals I given the model, and OT plus 1, T plus 2 all the way to the n all of T given Qt equals I and lambda. Okay, if you look at this probability and this probability, this is just forward variable that you compute up to the point T in the state I. This is just a backward variable that you compute up to the point T and I. Just these two multiply. So if you compute forward variable and backward variable, like forward to the point T and I state, backward to the point T and I state. These two compute, it'll give you this probability. Okay, now we just need to normalize by the total probability. So what's the total probability? Just P of O given lambda, just sum over I, right, from 1 to n. So all possible states in that it accounts already for the total probability. You sum it up, okay, then that's basically sum up I from 1 to n alpha ti, beta ti. And this is just problem 1, right? Okay. So if you look at this, what you can tell, the problem we say if you find the probability of O given lambda, you roll till the end, okay, for forward algorithms and sum up at the final state. Or backward algorithms is roll all the way back to the origin of the time and sum up at the first time. But if you have forward and backward all together, okay, at any point t, right, as they meet, just sum up that particular point of alpha. These two multiply over all the state, you get the exact same answer. So you have forward algorithm and sum of all the probability up to this point, backward algorithm sum of all the probability up to this point. When they meet at the same time, sum it up, you actually get the total probability observation. Okay, so and keep that in mind as well. So anyways, once you have this VT of I, the probability at time t or in state I is just this divided by this. So VT of I equals just alpha ti multiplied by beta ti divided by the total sum. Okay, if you look at this, it should make intuitive sense, right? We're trying to compute the probability of the model that you're in at time t, you're in state I. What's that probability? Right? It's just the ratio between forward algorithm up to the time ti state, backward algorithm up to the time t state I divided by the total within that time, right? So it's a ratio between the probability sitting from I state divided by the total probability of that particular observation. So it'll give you a ratio, and then basically tells you the probability at time t, whether the probability you're in state I. Okay. Anyway, so this is one way we can compute. So I introduce another variable. We can compute for every time, for every state, there's a probability. Okay, if you look at this, right, for every time, sum up you take this thing and you sum up all the state I from 1 to n, give you 1. So because you sum up all the things that give you 1. Anyway, so keep this in mind. It's just a probability of Qt here in state I accounting for an entire sequence. So anyways, let's back to the problem. It's the property of being state at time t given the observation. So one particular way we can think about this issue is trying to find the most likely state sequence. Let's try to say, okay, over all time, right? Look at every time step, argmax over the state number, which state is most likely out of this v t of I, right? Finding the which I within each of the t give you the largest value of b. Okay, that's one way to find the most likely state sequence within this HMM. Okay. So we kind of stopped here last time because the problem of doing this is intuitive, makes sense. The problem of this is becomes a problem. The resulting state sequence may not be valid. Say you do find qt of I, qt plus I equals to j. Okay, this one at time t, I is the largest. At time t plus 1, j is the largest. But you can run into a situation where actually the transition between I to j may be invalid. So it's not a valid transition. Okay? Although individually they are most likely. But this sequence actually do not happen at all. Okay, so this particular transition cannot, because the problem is because of this signature. Right? Because when you compute the forward variable, right, when I'm in state j, I account for all possible probability I go there. So it's a sum over all possible ways I can get there. So maybe one of the aij is 0. Okay, but the rest of them give you a large value. So that makes this thing large. Okay, so there could be one problem of when you find I and j, they're individually most likely, but that transition may not actually occur. Okay, now we're back to square one, right? So the problem now, how do we actually find the best state sequence? If you go back and say, okay, let's just loop through all the state sequence. Let's not do forward, backward, out. If you just loop through all the state sequence, find the largest. And that's the one way to solve it. But again, we cannot solve it that way. It's too many state sequences. So we have to introduce another algorithm here. We call it Viterbi coding or Viterbi algorithm. So Viterbi algorithm finds a way to find the best state sequence, or we call it this kind of called dynamic programming method. You find the best state sequence Q1, Q2, Q observational. We define another variable. Okay, this variable is the max over Q1 all the way to Qt plus 1 of the probability Q1, Qt minus 1 all the way up to Qt equals to I, O1 all the way up to OT given lambda. So we call this best score, okay, maximum probability along a single path at time t, ending in state I, accounting for all the first t observation. Okay, so you max, okay, you find the sequence, okay, up to the point t. Okay, what's the maximum probability? Okay, not the total probability. Okay, I don't care what's the total way I get to the state I. I only record the maximum probability that I will land in state I. Okay, these two are different concepts, right? So again, then by induction, okay, at the next time for each of the state j, okay, I'll look at max over I. Okay, this variable, right, probability, maximum probability up to the point t, landing in state I, and you're going from I to j, look at all those states, which one of this probability give me the largest, keep the largest, okay? You don't sum it up, you keep the largest, you take the max, okay? And then multiply 1 to t plus 1 minus plus this thing. So look at this thing versus four variables, this thing, okay? The only difference is we don't do a summation here, we do a max over I. Okay. Once you change the max over I, okay, what it does is every time you don't account for all possible ways you could land in J. You only account for the maximum way, the single way that you actually land in J, and then you actually look at that probability as the maximum probability. Okay, so this total probability and the diagonality with the maximum probability. Let's keep in mind, right? Maximum probability does not mean that's what happened. It's just more probable it has happened, right? So if you want to look at all possible ways, right? All possible probability of going there, you have to do this summation. When you do max, okay, it just gives you one single realization of, this is, the most likely in terms of probability that you get to state J. And keep in mind that does not mean the actual state I go to J. It's just more likely it's come to J. And then we record that. Okay, so So again, the variable from this is we call it delta t plus 1j, max over I, right? Max over I. This delta ti going from I to j. Look at at time t, all the state when you actually transit to j, which one is the largest value? Okay, keep that I. Okay, multiply that when you're in t plus 1 to j. Okay. Now, how do I know? Okay, where I come from, right? So this gives you the probability. Okay, you still also need to record. Okay, where I have come from, right? At this j, right? I know. Okay, this value is the largest probability up to the point t plus 1 landing in j. Okay, but I need to know where I have come from because I'm taking one of the previous state, which is the largest value to have landed here. So if it's state 2, give me the largest value. I need to store also, this is the largest value, and the previous state that gave me this largest value, I will transit to the state j is 2. Okay, we need to store that as well. Okay, we'll keep this in mind first. We'll list out the entire algorithm. Then you do that for every state, every time, until the end. Okay, and then you can backtrack to actually find which state sequence that is. So the actual algorithm looks like this. To initialize, have this probability. Okay, pi I, bi or 1, right? This is the initial state probability. Once you're in that particular state, see the observation or 1. You have another pointer we call pi I. Okay, it says 0 because it's initial, nothing. Okay, do some recursion. This delta trying to find the max, right, over 1 to n, right? N different states, right? Delta t minus 1i, aij. Okay, right? So this probability, right, is the largest probability that you could land in j I state at time t minus 1, and you're transiting to j state. Okay, and you look at over n different state, which one is largest, and then do that, keep that probability going, and multiply by bj, right, at the time t, right? You're in j state, see the observation only. Then you also do store here, store the argmax of this thing. Okay. So you have come from a single path, a probability that's largest, landing in I state t minus 1 time. You transit from one of the I to j. Okay. You look at which one of those give you the largest value, record that index. Okay, so this tells you the maximum probability that in this state, in this time, what's that probability? Okay, this tells you if you landed there with that probability, where did you come from in the previous step? Okay, and store that. Okay, then once hit to the end of the sequence, okay, then you find a probability, right? At the end of the sequence, you have this thing, right? Delta t over delta t of I going through all the states. Okay, you look at which one is the largest. Okay, and you look at that which one is largest. Say, the first state maybe this number is largest. Okay, then that number we can look at. Okay, restore what is that, and look into it. Say, okay, where did you come from? If you come from the previous time point, the second state, that gives the largest value so that you land in the first state. Then you can go to the previous time point, the second state. Okay. Within that second state, you have the largest probability. Okay, you store where you come from in the t minus 2. Okay, then you go back and then all the way back to the beginning of time. Then you trace out the most probable state sequence. Okay, through by storing this. We'll work out an actual example just to give you a sense. So how do we retrieve the state sequence? We just through backtracking. Okay, then you can find a state sequence that yields the P or P star. Okay, so note that this algorithm, right, it performs what is said maximization over all path states. Okay, you look at the most probable single state that will land in the next time point, certain state. Okay, it doesn't account for every possible ways it could land to one of the j state next time point. It only look for one of the n state that give me the largest value, and I only record that. Okay, so we call this maximization. Okay, finding the one that maximize the probability of a particular state sequence. Okay, Again, idea should be simple. Okay, you gather everything you need to know from all the past sample to the previous time point, and you move one step at a time to look at the largest value and where you did come from and backtrack it. And let's try to work on an example. Consider you have a coin tossing game with one of the three coins. So again, three states. Okay, model with three states. The possible observations are HT. Okay, let's say this is the BJO, right? So basically the observational probability. When you're in state one, it's a fair coin, so probably a head and tail D50. State two, probably head and tail, 75-25. State three, 25-75. Okay. You have an initial state probability that's just 1/3 for everything. So one of them could be easily likely to start. Okay. So again, they could easily, sorry, this is AIJ is a transition matrix. So every state, they're equally likely to transit to one of the other states. The I is the initial state probability, they're all equally likely. Okay, just keep things simple. So you have initial state probability, all equally likely. Transition matrix, equally likely. You have three different states. Okay, now we have this problem set up. Now somebody tells you the observation is head, tail, head. Okay, now we need to use Viterbi algorithm to find the most probable state sequences. Okay, we can exercise that algorithm. Okay, let's try to use it with Viterbi algorithm. So let's initialize, right? The first time, right, you have delta 1, 1, 1, right? It's index of time, three different states, 1, 2, 3. Okay. When you're in the first state, right, just initial state probability at the first state, output probability that when you're in the first state, seeing observation 1, right? So that's 1/3, right? We know pi1 is 1/3, B1 of head, right? B1, the first state, we know it is a fair coin. So we're in state 1, seeing a head that's 50%. Okay. So delta 1, 2 is, again, repeated, basically 75%. Delta 1, 3 is basically 1/3 of 25%. Okay. Initialized by 1, 1, by 1, 2, by 1, 3. Okay, they are all equally likely to start at 0. This is where I'm trying to record where I have come from, which is the largest value, but I'm at initial step, so I don't have anything to record. Okay, let's do t equals 2. Okay, time 2. You're in a state J. Okay, we want to find max, right, over all possible states, right? 1, 2, 3 plus 3 different states, max over one state. Delta 1, okay, the first time, right, the previous time, right, I state and go through I transiting to J, and at J equals to O2. So let's forget this, okay. J came from 1, 2, 3, right, three different states at second time point, okay. When the second time point, you're in the first state, we want to find the max over the first variable, right? The delta 1, the first time, the I state, where I can go from 1, 2, 3, and they all land in the first state, right? So again, delta I is the previous one. Okay, one of them will go to the first state at time t equals to 2. Okay, then we look at this computation and find the max. Okay, because there are three different numbers here, right? All of them are 1/3. So want to find this thing multiplied by this thing, right? And then pick the one that's largest. Okay, and store and multiply by, now you're in state 1, the second observation, right? Second observation is still head, I think. It's still head, so it's 50%. Okay. So what's the max value of this thing? It's just 75 times 0.5. Okay, so your delta 2, 1 equals 75 and 0.5. You have another variable that's stored. If you're in second time, if you land in first state, which is the most likely that you have come from? What's the max of the previous state that you come from? Okay. So one of these things gives you the largest value. Which one gives you is 2, right? You store 2. Okay, so this variable tells you the maximum probability landing at time 2, okay, state 1. Okay. Repeat for all the states, right? As time 2, state 2, again, max over previous, this kind of delta variables multiplied by all the I go to the second state now in time 2. Okay. Multiply by, now you're in the second state, seeing the observation that you see. Okay, again, then it's max over this thing, okay, multiplied by, now you're in head, and this is a head bias. If you're in state 2, it's a head bias, probably observation is 0.75. You have this thing. Then you can record, right? max over this thing, which one gives you the largest is this one. Okay, so then you put it 2 here. Okay, again, repeat third one, right? Still you're in time 2. Now another state you could be in is the third state. Okay, what's the maximum probability that you will land in third state in time 2 is the maximum probability from the previous time, all those possible states. All those possible states have to go to 3, so there's 3 different options. Okay, multiply by now you're in the third state, seeing the second times observation. Okay, so this is a tail bias coin. If you see a head, that's only 25%. Okay, and it's max over this thing. Okay, so because this is always the same as the AI, this AIJ, we set it equal, right? So it's 0.5 to 75.25. Whilst the max value of this thing is 7.75. Okay, now you can record at the second time. Okay, t equals 2. When you are in third state, this particular largest value had come from the previous time, the second state. So you record 2 here. Okay. Now you repeat this process. Okay. For t equals to 3, right? Again, t equals 3 is right, delta 3, right? In the time 3 in a particular state, j can go from 1 to 3. Okay. The max over different states. Okay, the previous delta. Okay, so delta now this is 2 the second time. The only 1 times that before. All those i's now go to the j. Only record the one that's largest. Okay, keep the largest, the max, because there are 3 options. And one of them will give you the largest option. Okay, multiply by now you're in j state. Okay, this is the first one, the fair coin. Seeing the third times observation, what that is. Okay, so again, is this max over this multiplied by this thing multiplied by this thing, and this thing to square this thing multiplied by this thing, and this is 0.25. Okay, so max over this thing, which is largest? This one is largest, right? So it's this thing multiplied by 0.2. It's 0.5. Okay, this variable try to store. Okay, which one of this give you that max? So it's R max of this. Okay, so it's sort of 2. Okay, so now you repeat for everything, still 2 and 2. Okay, with that you can actually write down the entire table. Okay, write the entire table, right? At P from 1, 2, 3, 4, 5, 6, right? This is the observation you're given. Head, tail, head. Okay. State 1, state 2, state 3, right? This is the delta variable, and we call this sort of a storing of where I come from. Okay, the address variables. Okay, again, this is state 2, this is state 3. Okay, for all the observation, and then this is initial. Okay, finding. Okay, where I have come from. Okay, now this one is the largest value. Okay, that I know I actually come from this state previously. Go to here. Okay, it'll give me the largest value, and I store this largest value of max. Okay. Repeat for all the states. Okay. Repeat for all the time. Okay. For all of these things, trying to record. Okay. If I have this probability being restored, what's where I have come from in the previous state? One of the 3 states will go in here. Okay. And which one give me this largest value? And again, same thing here. Okay. Which one give me this largest value? Find which one of this give me this largest value. Which one of this give me largest value here? All the way to the end. Okay, now you're at the end. You have this probability, and this probability. Okay, now we first need to pick this largest, or this is largest, or this is the largest. Okay, so it looks like I no mistake. The last one is 1, right? This is the largest. Okay, right. So the last state is 1. This compared to this and this is largest. Okay. So I know this is largest probability. I look at how I got here. Which of the previous state, okay, that will give me this largest probability. I look at this variable, 3. Okay, so it tells me here, okay, and this is the where I actually come from. Okay, so 3. Okay, once you're in here, okay, this is the largest probability you see. Okay, then you actually look into this one and say, okay, where I have come from to give me this largest probability. Look at it as 2, and you go to 2. Okay. Now this is the largest probability. And you look at where I actually have come from one of the previous states. Okay, and say 2. Okay, then you jump back to 2. So then you backtrack and decode them most probable state sequence. Now it's 2, 2, 2, 2, 3, 1. Okay, so under this scenario, when you see head, tail, head, okay, your friend has these three different state of the coin. It's throwing head bias, tail bias in a fair coin. And that most probable describe a single best path through this stuff. And then this is, doing the computational complexity, the same thing as Forward algorithm, okay? Because you're doing one step at a time, one step at a time, one step at a time. Okay, the only thing that's different from this to Forward algorithm is every point here you record the largest value. You don't sum up all the probability that come to here. You look at which one of this give me the largest value, and then store where I come from. Okay, and then repeat for all these things until hit the end, and you backtrack. Okay, then you get the actual best state, most likely state sequence can be decoded. And this we call the Viterbi algorithm. Okay, these are very efficient algorithm trying to find the most probable state sequence given the observation with the Peter-Markov model. And we'll talk again. It's about time now. We'll talk more about this and use it also later for continuous speech recognition. Speech recognition problem. And then one thing I want to mention here, if you look at this string, right, you can quickly spot this will be very fast implementation. Okay, if you write things in C, right, because you don't need to actually store the value. You actually look at the address. Right, just store the address where the pointers point to the address where it actually have come from. So writing this thing can be a very fast routing, and then this algorithm can run really fast in terms of Viterbi decode. That's why it's actually being used in communication, because this in computing is real time decoding of the possible zeros and ones. Okay, it can be done really fast with almost zero error. So you can just keep this in mind. Okay, so make sure you understand we have introduced many different kinds of variables. So I'm going to talk about forward algorithm that catches all probability up to the point. Backward algorithm catches all probability back from the end to this point. Okay. Or you can have a probability that talks specific about the probability you're sitting in one of the states accounting for the entire observation. This delta t I talks about the maximum probability that you land in T of the state I. Okay, it doesn't tell you all probable ways getting there. It tells you the most likely way of getting there. And this phi T1, okay, tells you if you're in this time for that particular state, you actually have come from most likely from from which previous state that you have come from. Okay, and then putting this together, then you have this Viterbi.好，我们今天先讲到这里。